Okay, sorry for the quick cut yesterday. There were technical difficulties and it was the best place to cut. I want to finish the notes. There's one last thing at the bottom called Taylor remainders. Now, a Taylor remainder is basically, or Taylor error, it's how accurate your Taylor series is going to be and how to find out what that error from the actual value can be. Now, obviously, your error is going to be smaller if you pick a number closer to the one you're approximating. For example, if I'm using sine of 0 as my baseline, sine of 0.1 is going to be more accurate than sine of 72 radians, which is obviously very far away. But we can look at that. It's this awful formula here where it says the remainder of x is the n plus first derivative, plugging in some value z, divided by n plus 1 factorial, times x minus c to the n plus 1. Now it looks scary, but remember, in order to get the Taylor series or Taylor polynomial, you already had to take the first n derivative, so it's just the next derivative after that. So let's look at number 7 on page 9.6, or number 7 on 9.7, it's on page 6. It's a tongue twister. Determine the accuracy of the approximation of sine of 0.1 using the third Maclaurin polynomial. Okay, so we know our function is sine of x. We need the derivatives. So the first derivative, cosine x. Second derivative, negative sine x. Third derivative, negative cosine x. And to the fourth derivative, we'll do this because we're going to need it for the remainder, back to sine of x again. And what are we plugging in? 0? So f of 0 is 0, 1, 0, negative 1. I don't need to plug it in for that one because we're just finding the polynomial right now. Okay, so that means my constant term is 0. My first one with an actual term is 1 times technically x minus 0 because it's a Maclaurin series. I get another 0 here, so it's still 1 times x minus 0. But my third Taylor polynomial, I get a negative 1. Now this is going to go to the x cubed term. This is 1 over 3 factorial times x minus 0. This should be a minus, not an equal sign. So if I expand this out further, this is x minus 1/6 x cubed. Okay, so this is the polynomial, but we really want to determine the accuracy of this polynomial if I was to plug in 0.1. And to do that, I need to find my fourth derivative evaluated between c and x. So the fourth derivative is sine of x. And we know the fourth derivative of sine of x has got to be between, because of the way sine works, it's less than the fourth derivative plugging in 0.1. It's greater than the fourth derivative of plugging in 0. Because those are my bounds. It's between 0 and 0.1. So what is sine of 0.1? Well, we know it's small. We know this whole thing is going to be less than 1 because sine is never going to be greater than 1. So this remainder is going to be sine of z, generally, because it's a sine function, divided by the fourth term, so that'd be 4 factorial, times x minus c, so 0.1 minus 0 to the fourth. Now, sine of z, 4 factorial is 24, times 0.1 to the fourth is 1/10 to the fourth, so 1 over 10,000. So this is equal to sine of z over 240,000. Now, we know that for all values of z, they're going to be between 0 and 0.1, but just generally speaking, we know that this is less than, because the sign is always less than 1 over 240,000. Now, what does it mean to be accurate to less than 1 to over 240,000? Well, every 0 is a decimal point, so it's accuracy to 1, 2, 3, 4, really 5 decimal places, and then some. So it's accurate to about less than 1/10, hundredths, thousandths, 10,000ths, 100,000ths. It's about this, because it's a little bit bigger than or smaller than 200,000. So the error is less than 0.000005, even with just this. And that's only because 0.1 is close to 0. Now you can see what it actually is if we plug it in. So what is our Taylor series? It's 0.1 minus 1/6 times 0.1 cubed versus sine of 0.1. So we'll put it into the calculator. So this thing is 0.0998333333. What is the sine of 0.1? It's 0.09983341. So you can see we said how many decimal places we were accurate to. 1, 2, 3, 4, 5, 6. Like, we were even more accurate than this, just implying that z was not, actually 1. We knew it was going to be less than that, but that's how crazy accurate we were, even with just this, because we were close. So this is an idea of what a Taylor remainder does. It tells you how accurate you're going to be. I'll leave the other one for you to do, just to make sure that when you're doing it, for the ln of 1.2, you should be approximating around 1, which it tells you in there. So just remember that it's going to be, instead of just x minus c when you're doing it. Otherwise, have a nice weekend.